Uh, Today's subject is verification and validation. We will talk about how to validate and verify a software product. Our objectives are to to introduce software verification and validation and to discuss the distinction between them. Further, we will describe the program inspection process and its role in verification and validation. We will also talk about the static analysis as a verification technique, and we will finally talk about the clean room software development process. Okay, we will cover today verification and validation planning, software inspections, automated static analysis, and clean room software development. From our former discussions, you also know that verification is the answer to the question, are we building the product right? Here, our main goal is to check out to see whether the software conforms to its specification. And validation is the answer to the question, are we building the right product? Here, our main goal is to check out to see whether the software does what the user really requires, user really wants. So these two questions are similar to each other, very similar to each other, but have totally different meanings. So this is the difference between verification and validation in a very short and concrete description. But you will see in the flow of this discussion the details of how verification and validation differ. Verification and validation process is a whole life cycle process that from here I would like to remind you of the V model development. I hope you remember when I say V model development, I hope you remember the diagram of it, the V shaped diagram. Verification and validation has two principal objectives: the discovery of defects in a system and the assessment of whether or not the system is useful and usable in an operational situation. So, well, these two remarks are extremely important. For example, I was reminding you of this since the beginning of this class, that it is a whole life cycle process. Validation starts with the with the requirement specification activity. I am sorry, and this is the point where the tests are started to get planned, etc. Okay. Here you see again the V model, the diagram of the V model development. As I said, the test plan is started as early as at the requirement specification activity. Well, at this point, towards the end of the requirement specification, we start to plan the acceptance test. Okay, this is the point. This is the document that describes what should be the standards of the acceptance test. Further, the system specification is an activity that supports the preparation of the acceptance test plan. As we proceed in the software development process, we also go into the into the details of the testing. For example, towards the end of the system specification and at the early stages of the system design, we plan the system integration tests. Because at this point, we have the knowledge about what subsystem the software product will be composed of and how these subsystems will be connected. As we further proceed in the software process, we now start to plan the subsystem integration tests. Okay, because at this point, towards the end of the system design and start of the detailed design, we now know what each subsystem will be composed of, what modules each subsystem will be composed of, and how we ought to connect each subsystem to or integrate each subsystem to the whole system. Okay. Well, at this point, with the end of the detailed design and the start of the coding, we should have come to an end with the test planning. And at the end of or during the development or during coding, we also start unit testing. So this is the point where we perform. This is the point where we perform unit testing. And after coding and unit testing, you see the tests starting from subsystem integration towards the acceptance is executed regarding the test plans prepared in the earlier stages of the software process. And after the acceptance test, of course, you see that we deliver the product. Any questions so far? If any questions, please write from your chat panel. I can also unmute you so that you can speak if you like. Okay. Here at this slide, we see what our verification and validation goals are. Verification and validation should establish confidence that the software is fit for purpose. This is our ultimate goal in performing in the verification and validation activity. We should create this confidence. We should establish this confidence for the customer that the software is fit for its purpose. Verification and validation does not directly shoot for completely free code. Okay, it doesn't that we're gonna perform a successful verification and validation activity does not necessarily mean that it will be the code will be totally free of defects. This is not the case. This is too hard to attain. This is too hard to reach a goal. Rather, it must be good enough for its intended use. So this will uh, this will uh, this will show the VNV activity show to the customer that whatever the software is intended for, it will be able to do this job, it will be able to fulfill this job in a successful manner. So this to make up, to show this confidence, to be able to establish this confidence is extremely important for the customer. Rather, it must be good enough for its intended use, and the type of use will determine the degree of confidence that is needed. Okay, let's see what the VNV confidence in some more details is. VNV confidence depends on the system's purpose, user expectations, and marketing environment. How so? Well, let's look at the software function. The level of confidence depends on how critical the software is to an organization. As you may well understand, that the confidence for the software product, the confidence required for the software product should be much higher for a safety critical system than that required for a prototype, for example, software system that has been developed to show some new idea. Okay, so it software function is, from the viewpoint, a factor that determines the confidence, how how critical the software is to an organization. Okay, if it's a safety critical system, for example, then it's the confidence required should be much higher, because people should depend on the safety critical system. But if it's a prototype system that should show a new idea, for example, then the confidence required shouldn't be as high as that of a safety critical system. User expectations is another factor that determines the level of confidence. Well, users may have low expectations of certain kinds of software, for example. Let's see, if it's a game software, for example, the user expectations may not be as high as a safety critical system. So another factor is the marketing environment. Getting a product to market early may be more important than finding defects in the program. Let's assume that you are a company, you're a software company, and you're trying to get a product to market, and this product is a very new in its idea. There is no such software brought up to the market beforehand. So that means that getting your product to market early would mean too much to you, because this will be the first one in the market. So that's extremely important, and you want to do that. So that means you may trade off in the confidence of the product, because you want to put it into the market as the first one in its class. So you may trade off. You may be a little loser. Not, I mean, you may compromise on making verification and validation a little, so that getting this product to market as the first product should be you should be able to do that. Okay. Another thing about as a factor of the marketing environment that affects the confidence is that a customer willing to pay a lower price to your software product possibly means that the customer is tolerant to more software faults. So then you may again compromise a little on the verification activities. Okay, so from the viewpoint of the marketing environment, then two things are important. One, you can compromise at your verification activities if you wanna put your software product to the market as the first product in its class. And the second one, if the customer is willing to pay a lower price for your product, then he or she should be more tolerant to, or he or she should be tolerant to more software. About the static and dynamic verifications, we have talked about that, about the difference between static and dynamic verification before. Let's remind it. Let's remember it. Software inspections were the static verification techniques, and they were concerned with the analysis of the static system representation to discover problems. Here, you don't run the software. A software inspection is an activity that is performed on the documents of the software product, but not on a running version of it. As opposed to that, software testing is the dynamic verification technique, where a running version, an executable of your software product is required. It is concerned with exercising and observing product behavior. Here, the system is executed with test data, and its operational behavior is observed. So you have test data, you run your system using this test data, and you take the test output, you take the output and you compare it with your expected output. Please, if you have any questions, let me know. Either write through the write through the chat panel so that I can see and unmute you. Okay, this is the this is the diagram of the static and dynamic verification techniques. So the arrows indicate here the stages in the process where the techniques may be used. So, for example, you can use the software inspection at each activity here in the software development process. But you can use the program testing only on the executable versions of a program, either on a prototype or on a program. So this diagram here nicely clarifies the different activities of the software process, where the software inspection and program testing, or in other words, static and dynamic verification methods can be used. In the program testing, about the program testing, it can reveal the presence of errors and not their absence. So assume that your software, your piece of code has passed the tests that you have performed. It doesn't tell you, it shouldn't tell you that it is error-free. Okay? But if the tests, there are some tests that your piece of code didn't pass, then these tests reveal the presence of errors. All right, so it is a psychologically destructive activity, the testing activity, or in general verification activity, is a psychologically destructive activity. Why? Because it can, your piece of code may pass all your tests, but this shouldn't necessarily mean that your software is free of errors. Okay, but if there are some tests your piece of code failed, then it definitely shows that there are some errors present in your code. The only validation technique for non-functional requirements as the software has to be executed to see how it behaves. So, well, you can, using the static verification techniques, using the software inspections, you can find out some errors in the code, okay, or in any of the documents prepared at these activities, at any of the activities in the software process, but you cannot find out anything using software inspection about the non-functional requirements. Why? Because, okay, because non-functional requirements mostly require a running version, an executable version of your program. Otherwise, you don't understand whether or not the non-functional requirements of the software product is met. I'm sorry, are met. Can someone tell me the only exception of the non-functional requirements, what the only exception of the non-functional requirements to that expression is? What I'm talking about is, what is the only non-functional requirement that can be determined, that can be assessed using software inspections? Can someone suggest what this exception to non-functional requirements are? The only system property that can be assessed using software inspection and not program testing. What is this system property? Any suggestions? Can you write on the chat panel? We have discussed that before. What is the what is the only static system property? What is the only static software property? That is the one that can be assessed using the software inspection, and it doesn't require execution of the code. Can someone tell me that? Okay. Well, let me tell you then. It is the maintainability. Maintainability, if you check maintainability, is assessed by the documents, either requirement specification documents or design documents, also mostly on the source code. Okay, for example, the more modular should be your code so that it is more maintainable. That means the more maintainable you want your code, the more modular should be your code. It should be composed of more modular, that is finer pieces of code. Okay, program testing is program testing also should be used in conjunction with static verification to provide full verification and validation coverage. That means that program testing, that means that the dynamic and static verification techniques are supporting each other. They should be used. They are complementary, and they should be used together. Okay, so that a full verification and validation coverage can be attained, can be reached. Let's look at the types of testing. There are two types of testing from their functionality viewpoint. The first one is defect testing. Here the tests are designed to discover system defects. A successful defect test is one which reveals the presence of defects in a system. That's why I told you in the previous slide that testing is a psychologically destructive activity, because a successful defect test actually shows an error in your system. So something that you have to locate and correct. Another type of testing from the functionality viewpoint of testing is validation testing. It intends to show that the software meets its requirements. Okay, so this is more like a testing that is performed in the guidance of the requirement specification document, because the requirement specification document tells you what requirements are there for the code to perform, to meet. Here, a successful test is one that shows that the requirement has been properly implemented. Okay, now validation testing, as opposed to defect testing, is not there to show system defects, but if a validation testing piece has is passed by your program, then that shows that the requirement has been properly implemented. Okay, so that's a good thing if a validation test is passed by your program, passed by your software product. Please ask any questions if you have any by writing from your chat panel. Okay. Now, as to the testing and debugging, what are they? Defect testing and debugging are two distinct processes. Verification and validation is concerned with establishing the existence of defects in a program. That is, testing and static verification. They are both concerned with establishing the existence of defects in a program. These are not debugging, verification and validation. Debugging, on the other hand, is concerned with locating, finding out where, and repairing these errors. So VNV or tests, VNV and tests okay. VNV and tests are to reveal defects in the program, and debugging is to locate them and repair these errors. Debugging involves formulating a hypothesis about program behavior, then testing these hypotheses to find the system error. Okay, so VNV and debugging are two different things, or testing and debugging are two different things. Testing is used to find the error. I'm sorry, testing is used to reveal the error, and debugging is to find the errors location and repair these errors. Okay. Now this is the debugging process. Here we have as input to, okay, we have the test results. From the test results, we try to locate the errors. Once we locate the errors, we design the error repair regarding the specification document. We repair the error, retest the program using the test cases, and if the test results are now okay, then the program means to have passed this test. Okay, as to the verification and validation planning, careful planning is required to get the most out of testing and inspection processes. So we have to plan the testing activity in a careful fashion. Planning should start early in the development process. So again, this remark should remind you of the V model development. All right? The plan should identify the balance between static verification and testing. The plan should identify the balance between static verification and testing. So we have in the previous slides, I told you that static and dynamic verification techniques are complementary. You should use both to provide a full verification and validation coverage. So this remark, this third remark, reminds you of that. The plan should identify the balance between static and verification, static and dynamic verification. Oops. Test planning is about defining standards. This is also an important remark. Test planning defines standard for the testing process. It doesn't describe the product tests. It describes the standards for the testing process. This is an important remark. Please keep that in mind. When you do test planning, that means you are defining the testing standards, all right? You don't describe the tests, individual tests. Again, as I said in the second remark, you should remember the V model development when you read this. Planning should start early in the development process. Again, I put here the V model development to remind you of that. A validation starts here, okay? So validation means the planning of the testing process starts at the very early activities of the software process. Okay. Well, about the structure of a software test plan, the testing process, requirements traceability, tested items, testing schedule, test recording procedures, hardware and software requirements, and constraints of the test. So I told you here in this VNV planning, as the last remark, I said that test planning defines standard for the testing process. Here you go. The structure of a software test plan is this. These are the steps of test planning, all right? When you plan a test, then you have to explain the process. You have to look at the requirements traceability to to specify what this test is concerned with what requirements this test is concerned with. Tested items, which items should be tested? You should clarify this. You should tell the testing schedule. You should say how the recording of the test procedures will be. What are the software and hardware requirements? And finally, what are the constraints of the test? In the planning of a test, you should clarify these points. Okay. Here, each of the points here is explained in this slide. Testing process is described here under this title, a description of the major phases of the testing process. These might be as described earlier in this chapter. Requirements traceability. Users are most interested in the system meeting its requirements, and testing should be planned so that all requirements are individually tested. So one thing I want to show you again is this one here, requirement specification, okay, and system specification. Okay, you prepare the acceptance test plan and system integration test plan. In both, the users are most interested in the system meeting its requirements. So this is a functionality testing and a validation testing. The second thing I want to show you is this. Validation testing. It is intended to show that the software meets its requirements. Okay, so requirements traceability, another important parameter of the testing plan. Tested items, the products of the software process that are to be tested should be specified. Testing schedule, an overall testing schedule and resource allocation for the schedule. Test recording procedures. It is not enough to simply run tests. The results of the tests must be systematically recorded. It must be possible to audit the testing process to check that it has been carried out correctly. Hardware and software requirements. This section should set out software tools required and estimated for hardware utilization. And finally, constraints. affecting the testing process, such as staff shortages, etc., should be anticipated in this section. Okay. About the software inspection, these involve the inspection activities involve people examining the source representation with the aim of discovering anomalies and defects. The inspections involve people examining the source representation with the aim of discovering anomalies and defects. So you look at the documents, different outputs of the outputs of different software process activities, such as requirement specification, requirement specification document, or design specification document, or the source code itself, as you most probably did many times while you're preparing your project, and finding out here possible anomalies and defects by inspecting, for example, your source code or your requirement specification document. Inspections do not require execution of a system, so that's why we call inspections static verification techniques. So may be used before implementation. That means you can perform software inspection early in the software process. You don't need to implement your system because software inspections doesn't require an executable of your system. They may be applied to any representation of the system, requirements, design, configuration data, test data, etc. And finally, they have been shown to be an effective technique for discovering program errors. Well, you may have experienced how effective software inspections are when you looked at your source code of your different projects. It is a very effective technique. You look at your code and find out possible errors from your document, code, or any document. Okay. About the inspection success, there are two remarks here we have to go through. Many different defects may be discovered in a single inspection. In testing, one defect may mask another, so several executions are required. So this remark here is about a comparison between the inspections and testing from a success viewpoint. So while inspecting a document, you can find out an error, a problem, a defect by a single pass of this document, okay? But in testing, one defect may mask another, so several executions are required. In testing, on the other hand, well, you find an error, for example, but while this error is in the code, that might have masked, might have hidden another possible defect. So after you, at least after you have corrected this error, okay, you should rerun your code to see whether another problem has occurred at the uh, uh, near this error that you have corrected. Another remark about the inspection success is the reuse domain and programming knowledge are essential, so reviewers are likely to have seen the types of error that commonly arise. That means that in short means that if you are going to perform inspection, then you better be an experienced programmer. Okay, an experienced programmer, and you better should have seen, you better have experienced, have encountered these types of error beforehand. So the two remarks of inspection success is that while inspecting doesn't require multiple passes, testing requires several executions to find out possible errors that are masked by the by the first discovered defects. And the second remark is that inspectors, software inspectors, should be experienced on the types of error that commonly arise. Let's talk about the inspections and testing. They are complementary. We said that inspections and testing are complementary. They complement each other. They support each other, and not opposing verification techniques. Okay, both should be used during the verification and validation process. Inspections can check conformance with a specification, but not conformance with the customer's real requirements. Okay, so inspections, you can performing inspections, you can check conformance with a specification. That means that what code you have developed, you can check whether this code, this piece of code, conforms to the specification. This remark should remind you of the reliability of the software, okay? Because inspections check conformance with the specification. But inspections do not give you or provide you conformance with the customer's real requirements. So to be able to provide conformance of the code with the customer's real requirements, you have to have an executable of your code. Okay. So this here, the first part of this third remark should remind you of the reliability of the software, and the second portion of this third remark should remind you of the validation testing. Validation testing is functionality testing, and you need here an executable. Okay, and last remark is inspections cannot check non-functional characteristics such as performance, usability, etc., because to assess the non-functional characteristics, as I said before, you need an executable, because only your executable is can assess the non-functional requirements. Okay, here I stop. I take a 10-minute breaks and I stop the recording. Okay, we have mentioned the relation between inspections and testing. Now let's talk about the program inspections. Um, this is a formalized approach to document reviews, uh, and it is intended explicitly for defect detection. It is not for correction, but it is for defect detection. So you look at your you look at your source code and you try to identify some logical errors or anomalies in the code that might indicate an erroneous condition. For example, an uninitialized variable or some uh, missing portion of a loop that doesn't really come out in the compilation process, etc. So inspection preconditions. Okay, what do we need for inspection before it starts? A precise specification must be available. So this is a document that we need to base upon. Team members must be familiar with the organization standards. The second remark implies experience or experienced team members about the inspection. Syntactically correct code or other system representations must be available. So this third remark tells you that if you inspect a source code, then this should be compiler error free. Okay, this should have passed the compilation process. An error checklist should be prepared to cross-examine what problems you need to, as inspector, you need to inspect. Management must accept that inspection will increase costs early in the software process. So this is another important issue in the software companies. Management might look at the inspection as a unnecessary process. That's wrong, because management, for the inspection to be effective, first, management must accept that the inspection will increase costs early in the software process. Further, management should not use inspections for staff appraisal. That is to say, finding out who makes mistakes. All right, that is not a good approach for the management to use inspections to find out which programmer did what mistake. Okay, this is the diagram of the inspection process. The these these ellipses are the processes. It starts with the planning of the inspection, then an overview is performed, then individual preparation is done. Finally, an inspection meeting is performed, a rework is required then, and then a follow-up is required. And finally, the inspection process is complete. Okay, let's look at the inspection procedure. System overview is presented to the inspection team. Code and associated documents are distributed to inspection team in advance so that they can inspect at any document they find necessary. Inspection takes place and discovered errors are noted. Modifications are made to repair discovered errors, and reinspection may or may not be required after the errors are repaired. Okay, here you see here you see a, the inspection roles. Who is the author or owner, the programmer or designer responsible for producing the program or document is the author or owner. The programmer is responsible, or the author rather, is responsible for fixing defects discovered during the inspection process. Okay, who is the inspector? So author is the programmer. Inspector is the one who finds errors, omissions, and inconsistencies in programs and documents, may also identify broader issues that are outside the scope of the inspection team. Who is the reader? Reader presents the code or document at an inspection meeting. Okay, so reader is a meeting role, an inspection meeting role. Reader presents the code or document at an inspection meeting. Scribe is the one who records the results of the inspection meeting. Chairman or moderator manages the process and facilitates the inspection. It reports process results to the chief moderator. Oops, sorry. And oops. And chief moderator is the one who is responsible for inspection process improvements, checklist updating, standards, and development. So owner is the coder or programmer, and he is responsible for fixing defects. Inspector is responsible for finding errors or omissions or inconsistencies. Reader is the one who presents the code at the inspection meeting. Scribe is the one who records the results of the inspection meeting. Chairman or moderator manages the individual inspection process, and chief moderator is the one who is responsible for inspection process improvements, checklist updating, standards development, etc. So the chief moderator is a role who is responsible for a broader who has a broader responsibility. Okay. Well, we look here at the inspection checklist of common errors should be used to drive the inspection. So in the inspection checklist, we have to include the common errors so that it should be a guide for the inspectors. Error checklists are programming language dependent and reflect the characteristic errors that are likely to arise in the language. So each programming language has its own types of common errors. Okay, so whatever language a program is written on, this should have a programming language dependent checklist. And this should reflect the characteristic errors that are likely to arise in the language. In general, the weaker the type checking, the larger the checklist. So what that means is the weaker, okay, the less effective your compiler is, the less errors your compiler checks, the large becomes the checklist for the inspector. Okay, so for example, a compiler that performs a more powerful type checking leaves the inspector only a smaller number of checks to perform. Here, examples to type checking activities are initialization, constant naming, loop termination, array bounds, etc. These are very common. These are common problems to almost all programming languages. And in case a compiler checks most of them, then the inspector has less to do as far as the checklists are concerned. Okay. Well, we see several types of faults here that should be on the inspection checklist. For example, data faults are all program variables initialized before their values are used. Have all constants been named? Should the upper bound of arrays be equal to the size of the array or size -1? If character strings are used, is a delimiter explicitly assigned? Is there any possibility of buffer flow? These are typical data faults. Let's look at the typical control faults. For each conditional statement, is the condition correct? Is each loop certain to terminate? Or otherwise, some program crash may occur. Are compound statements correctly bracketed? In case statements, are all possible cases accounted for? If a break is required after each case in case statements, has it been included? About the input-output faults, are all input variables used? Are all output variables assigned a value before they are output? Can unexpected inputs cause corruption? This is an important I/O fault. And further faults, inspection that should take a place in the inspection checklist. Do all interface faults, do all function and method calls have the correct number of parameters? By interface, we mean the interface of methods or functions. Do formal and actual parameter types match? Are the parameters in the right order? If components access shared memory, do they have the same model of shared memory structure? Storage management faults. If a linked structure is modified, have all links been correctly reassigned? If dynamic storage is used, has space been allocated correctly? A very common error that many of us make. Um, and exception management faults. Have all possible error conditions been taken into account? Okay, so these are some types of faults that should be in the inspection checklist. Okay, this is an important slide. This gives us an idea about the inspection rates. During an overview, per hour, 500 statements can be inspected, 125 source statements per hour during individual preparation, and 90 to 125 statements per hour can be inspected. Inspection is therefore an expensive process. Inspecting 500 lines costs about 40 man-hours effort. So this is a clear indicator of how expensive inspecting can be. Inspecting 500 lines costs about 40 man-hours effort. So 40 man-hours means for one man, a week, an effort of a week. So that is about 2,800 pounds at UK rates. Okay. Now let's look at the automated static analysis slide. Static analyzers are software tools for source text processing. Okay. So these are tools, software tools that perform automated static analysis. They parse the program text and try to discover potentially erroneous conditions and bring these to the attention of the VNV team. Assume, for example, that you have an uninitialized variable. So you use a variable, but you didn't initialize it. So automated static analyzers are used to find, for example, this type of problems. If, for example, an uninitialized variable is being used in your software code, it inspects the software code and finds out that this variable is being used, but it is uninitialized. Okay, the third remark of the automated static analysis is they are very effective as an aid to inspections. They are a supplement, that is a supportive kit but not a replacement for inspections. You can use an automated analyzer, but still a human inspection, a software engineer inspection, a test engineer's inspection is invaluable. It's very valuable. Okay. Now the same faults, here we looked at what type of faults, uh, what type of questions we have to ask regarding these data faults in the checklist, and these are the static analysis checks for the same type of faults. For data faults, variables used before initialization, variables declared but never used, variables assigned twice but never used between assignments, possible array boundary violations, undeclared variables. Control faults, unreachable code, unconditional branches into loops. Input-output faults, variables output twice with no intervening assignment. Interface faults, parameter type mismatches, parameter number mismatches, non-usage of the results of functions, uncalled functions and procedures. Okay, and storage management faults, unassigned pointers, pointer arithmetic, etc. Okay, what are the stages? What are the steps of the static analysis? Control flow analysis checks for loops with multiple exit or entry points, finds unreachable code, etc. So data use analysis detects uninitialized variables, variables written twice without an intervening assignment, variables which are declared but never used, etc. And interface analysis checks the consistency of routine and procedure declarations and their use. Information flow analysis identifies the dependencies of output variables, does not detect anomalies itself, but highlights information for code inspection or review. And finally, path analysis identifies paths through the program and sets out the statements executed in that path. Again, potentially useful in the review process. All of these stages generate vast amounts of information. They must be used with care. So, okay, so static analysis provide us with a lot information. Well, the term big data is justified here. So we have to use these data with care. Okay, so this is a automated static analysis example. This okay. Up to that point, we have the input to the static analyzer. This here is the input to the static analyzer. Okay, and this portion here, we run the static analyzer, and here these are the messages that the static analyzer provides us. Let's look at this example. C may be used before set. Here says that we use C, but we don't initialize it. So this is the 10th line. This is the 11th line. Print array variable of arguments. Print array variable number of arguments. Okay. So Well, this tells us that print array is variable number of arguments means here I have three variables in the argument, and I have only one argument here in the argument list. So this is a problem, and it tells us this here, etc. So this is an example to static analyzers. Okay. Um, if you have questions, again, please let me know from the chat panel. Here we look at the uses of static analysis. It is particularly valuable when a language such as C is used, which has a weak typing, and hence many errors are undetected by the compiler. So for this, for example, programming languages with weak type checking facility, static analyzers are important. They're valuable. To use them is good for inspections or verification. And the second remark about the use of static analyzers are they are less cost effective for languages like Java because Java is strong in type checking and can therefore detect many errors during compilation. So that here from these two remarks, we can conclude that the use of static analyzers are the more cost effective, the weaker the type checking facility in a programming language is. Again, the more cost effective the use of the static analyzers, the weaker the type checking facility in a programming language is. Okay, let's look at the relation between the verification and the formal methods. Formal methods can be used when a mathematical specification of the system is produced. So in the beginning, we said that critical systems use formal methods, and since the requirement specification is extremely important for critical systems, usually a mathematical specification or a state-based specification is expected in the requirements, in the preparation of the requirements document. They are the ultimate static verification technique. So to come up with the requirement specification and to come up with a or to verify a critical system, static verification, or I'm sorry, software inspection is extremely important. Well, formal methods involve detailed mathematical analysis of the specification and may develop formal arguments that a program conforms to its mathematical specification. So it is important that the program of a critical system, for example, conforms to its mathematical specification. That's why verification in the formal methods involve detailed mathematical analysis of the specification. Okay. Now, arguments for the formal methods we produce a mathematical specification, and this requires a detailed analysis of the requirements, and this is likely to uncover errors. So that's a good thing because preparation preparation of the specification in a formal methods requires a detailed mathematical analysis. And this detailed analysis of the requirements probably will uncover errors. So since the preparation of the specification in a formal development method requires a detailed mathematical analysis, we can understand that it is going to be done with with more care, and this will likely uncover more errors than regular systems developed with other methods than the formal methods. They can detect implementation errors before testing when the program is analyzed alongside the specification. So using formal methods, that means you also use software inspection and static analysis. This may detect implementation errors before testing when the program is analyzed alongside the specification. So these are the two advantages of formal methods. Now, these are the three remarks that are against the formal methods. Formal methods require specialized notations that cannot be understood by domain experts because a detailed I'm sorry, a detailed mathematical analysis is involved. This requires specialized notations, which is not really understandable by the domain experts. So they can't understand the specification easily because detailed mathematical analysis is involved. Another disadvantage of the formal methods that is actually not exactly a disadvantage, but arguments against the formal methods. That formal methods are expensive to develop a specification and even more expensive to show that a program meets that specification. A third argument against formal methods is that formal methods may be possible to reach the same level of confidence in a program cheaper using in a cheaper way, I'm sorry, using other VNV techniques. So these are the three arguments. A clean room software development is based upon formal methods, and the name clean room is actually derived from the clean room process in the semiconductor fabrication. The philosophy is defect avoidance rather than defect removal. So clean room the name clean room implies that we rather try to avoid defects than remove them. The software development process is based upon incremental development, formal specification, static verification using correctness arguments, and statistical testing to determine the program reliability. Here, one remark is here, the second remark against the formal method, very expensive to develop a specification and even more expensive to show that a program meets that specification. This portion here, implies that attaining a higher level of reliability is very expensive in formal methods, okay? This is what the second portion of the second remark tells us. And we use statistical testing to determine program reliability. Here, we perform we assess the reliability performing the statistical testing. Okay, we also complement the dynamic verification method, statistical testing, with the static verification that is with the software inspections. Okay. This diagram here indicates us the clean room process. We formally specify the system. We develop an operational profile of the system. We define the software increments. Well, here, from the incremental development, we develop the software product incrementally. We define each software increment at this point, and we construct the structured program. We develop it here. We formally verify the cost, perform the statistical testing here, go back to the development for the possible errors, and then integrate the increment. And then, well, we test the integrated system. We test the system here as a whole, and then go back for possible error rework. And then from the software increments, here we design the statistical tests to perform these statistical tests to test the entire system. And this is the diagram how the clean room process proceeds. Okay, at this slide we see the clean room process characteristics. Clean room process uses in the specification activity formal methods using a state transition model. So the formal specification is used in requirement specification activity, and the systems model is made up of states and transitions. So it's a state and transition model. Incremental development is used to develop the system to convert the design into a into code where the customer prioritizes the increments. That's what we expect, of course, the prioritization of increments, so that we can put the increments in an order. Which increment is going to be developed first? Structured programming is an effective approach in clean room process. We have limited control and abstraction constructs are used in the program. We use static verification using detailed inspection, and we also use statistical testing. We also complement this software inspection with the statistical testing as a dynamic verification technique of the system. Okay, let's see at the formal specification and inspections, how they relate. The state-based model is a system specification, and the inspection process checks the program against the model. So we have at the end of the specification, actually at the end of the specification, we have the requirements, and these requirements are expressed, are shown as a state-based model, and then the state-based model is detailed in a into a state transition model, which is actually the design of the system, and then this design is converted into code using incremental programming. The programming approach is defined so that the correspondence between the model and the systems is clear. Here, mathematical arguments are used to increase confidence in the inspection process. Well, mathematical arguments as to this remark, please remember that the reliability in critical systems, we mentioned that the reliability as well as other system properties, some other system dependability dimensions can be defined as a probability. So that's why mathematical arguments are used to increase confidence in the inspection process. The more reliable you can prove your system, the more reliable, the more confidence is established at the customer side. Okay. Clean room process teams, there are three groups of, there are three teams to perform clean room process. Specification team responsible for developing and maintaining the system specification. Development team is responsible for programming and verifying the software product, and the software is not executed or even compiled during this process. This is an important separation between the certification team and development team. Development team only develops and verifies software, but the software is not executed or even compiled during this process. This is the job of the certification team. It is responsible for developing a set of statistical tests to exercise the software after development, reliability growth models used to determine when reliability is acceptable. This is also the responsibility of the certification team. So specification team specifies the software, development team develops and verifies the software, but not without executing or even compiling the code, and certification team prepares statistical tests to see whether the system meets its requirements, plus what is its reliability. Okay, clean room process evaluation. The results of using the clean room process have been very impressive, with few discovered faults in delivered systems. So it is an effective software development process model. Independent assessment also shows that the process is no more expensive than other approaches. This is extremely important. Let me underline this. Independent assessment. That is important. The people that are not affected by both the customer side and the developer side, they made experiments, and their idea is that the process is no more expensive than other approaches. This is extremely important. Please pay attention to that. Extremely important. In the beginning, we said that a problem, not a problem, but a disadvantage of the formal methods is that they're much more expensive. But independent assessment shows that they're no more expensive than other approaches. Okay. So another remark about the clean room process evaluation, there were fewer errors than in a traditional development process. So that's a very good thing that speaks for the clean room process development. However, the process is not widely used. It is not clear how this approach can be transferred to an environment with less skilled or less motivated software engineers. So the problem, there is a problem with using the clean room software development, and that's because in the sector, there are less skilled or less motivated software engineers that can use clean room process. So it is extremely important that you understand that clean room process is no more expensive than other approaches, because, okay, that implies that it may be used for development of any regular software system. So why it is not used is because it is not transferable to an environment with less skilled or less motivated software engineers. Okay. Well, here we have the key points, if you may. Verification and validation are not the same thing. Verification shows conformance with specification. Validation shows that the program meets the customer's needs. Test plans should be drawn up to guide the testing process. Static verification techniques involve examination and analysis of the program for error detection. And here, program inspections are very effective in discovering errors. Program code in inspections is systematically checked by a small team to locate software faults. Static analysis tools can discover program anomalies, which may be an indication of faults in the code. And finally, the clean room development process depends on incremental development, static verification, and statistical testing. Okay, so this is the end of verification and validation chapter. Do you have any questions? Now I will unmute you all. If you have any questions, please ask. Otherwise, I will conclude this discussion. Sorularınız var mı arkadaşlar? Peki. O zaman teşekkür ediyorum. Gelecek hafta Salı günü buluşmak üzere.